Okay, thanks everyone for coming today to the third seminar in our series. So today we're happy to have Brandon Rayhaun from SCGP, and he's going to tell us about an ode to half linking on symmetries, interfaces, boundaries, and junctions. And I'm really excited to finally hear about this paper.
Great. Yeah. So thanks a bunch for allowing me to speak here. As my title suggests, I'll talk about interfaces, boundaries, and junctions, mostly focusing on 1+1 dimensions, where things become a little more mathematically sharp, and how these things interact with generalized global symmetries. And this work is based on, or this talk is based on joint work with my two collaborators, Ichel and Junction. And if you don't like what I have to say here, they gave very beautiful talks, Ichel at IAS and Junction at Oxford. So I highly recommend you go watch those. They're on YouTube. And it turns out that several people sort of had very similar ideas to us. And so we ended up coordinating our paper with 4 other papers that were submitted to arXiv on the same day. And also there's some related works that appeared a little bit earlier. Good. So the sort of big picture motivation for this talk is that while historically there's been a prejudice in favor of local operators and local observables, as time has gone on, we've become increasingly appreciative of the importance of extended objects and extended observables. And part of this is due to the fact that they're implicated in tons of killer apps. For example, for a condensed matter physicist, defects of various codimensions could be thought of as impurities in your system. For a string theorist, boundary conditions are closely related to branes in space-time. Topological extended objects are, as everyone in the audience knows, intimately related to generalized notions of symmetries, and the list goes on and on. And so you might imagine that in each of these settings, it can be fruitful to understand how generalized global symmetries interplay with extended objects. And so the spirit of this talk will be to develop some generalities along these lines. Okay, so the rough plan of the talk is going to be that I'll introduce a sort of somewhat new class of algebras that encode how generalized global symmetries act on junction operators. And whenever you introduce a kind of symmetry structure in physics, it's fruitful to understand how your observables organize into representations of that symmetry. So to that end, I'll tell you a little bit about the representation theory of these algebras, and it'll turn out that it's very useful to appeal to 2+1D topological field theory techniques in order to do this. And in particular, in connection with this, I'll try to emphasize how these nice quantities known as half-linking numbers enter and allow you to do very concrete kinematic calculations, sort of in the spirit of character theory for finite groups. And finally, I'll apply some of this technology that was developed in sections 1 through 3 to the study of the annulus partition function of a conformal field theory. Good. So I don't think I need to remind this audience much about global symmetries in 1+1 dimensions, but just so we're on the same page, I remind you that symmetries in 1+1D are implemented by topological line operators and also junction operators between them. And in particular, if you have a finite collection of topological line operators that are closed under fusion, then those lines assemble into a mathematical structure known as a fusion category. And roughly speaking, the defining data of a fusion category are its fusion coefficients and also its some numbers known as F symbols that describe how to perform various recombination rules of lines connected by junctions. Similarly, if you have a 1+1D quantum field theory with some symmetry category C, then its various boundary conditions will also sort of transform in multiplets of the C symmetry. And mathematically, these multiplets are described by a notion known as a C-module category. So here, again, the defining data of a C-module category are some fusion coefficients, which describe the result of fusing a topological line onto the boundary condition. And a sort of analog of the F symbols, the module category F symbols that describe recombination rules for topological lines that terminate on the boundary conditions. Okay, so that's maybe all I'll say in the way of reminders. And then we can immediately jump into the sort of motivating question of this talk, which is what is the symmetry structure that acts on junction operators? So here, I imagine that I have some collection of quantum field theories, Q1, Q2, Q3, Q4. And each of them has maybe its own symmetry category, CI. And I imagine that there are, I have some interfaces that separate these theories. And I want to study the space of local operators which sit at the intersection point of these interfaces. So you might imagine that the symmetry categories of each of these theories should act in some way on these junction operators. And how can we make that precise? Well, for ordinary local operators, we've known for a while now that the most basic way that a global symmetry can act is by linking. So we take a topological line in this fusion category and we encircle the local operator with it and shrink the line onto it to produce a new local operator O prime. But actually, more generally, it can be sort of useful to consider a more general class of actions, which are known as lasso actions. And here, lassos allow you to act with global symmetries, not just on genuine local operators, but also on twisted sector local operators. So in other words, local operators that live at the endpoint of a topological line. And I note that these lassos in general will take you from a twisted sector local operator attached to a line A prime to a twisted sector local operator attached to a generally different line B. Now, by definition, what is known as the tube algebra is the algebra that's generated by these lasso diagrams. And because of this fact that it can sort of change the twisted sector that the operator belongs to, it doesn't quite act on a single twisted sector, but rather it acts on the extended Hilbert space, which by definition is sort of the direct sum of all the twisted sectors of the theory. So we can imitate this idea for junctions pretty straightforwardly. So again, assume you have some collection of QFTs with symmetry categories CI. And let's also assume that we have some multiplets of interfaces between QI and QI plus 1. By a multiplet of interfaces, I mean a sort of collection of interfaces that transform into themselves under the action of CI from the left and CI plus 1 from the right. Mathematically, this is what's known as a CI plus 1 bimodule category. And so here we can define these sort of generalized lasso diagrams where they sort of eat a junction operator and then spit out a new junction operator essentially by, well, morally you're encircling the junction operator with symmetry lines, but you just have to be careful about specifying various topological junctions where the lines meet the interfaces and so on and so forth. Anyways, these algebras that are generated by these lasso diagrams are a sort of general class of tube algebras. And I just comment that these tube algebras don't depend on the sort of details of the interfaces in these multiplets. Rather, they only depend on how these multiplets, how these interfaces transform with respect to the symmetry. So in other words, these tube algebras sort of only depend on the structure of these multiplets as bimodule categories. And again, because these lassos have this funny property of mapping junction operators attached to certain conformal interfaces to junction operators attached to other interfaces. So here you see that I1 prime is changed to K1, for example. These tube algebras don't quite act on a single junction Hilbert space, but rather the sort of direct sum of all of them. So we'll use this notation to denote the extended Hilbert space of junction operators. Are there any questions so far about the definition of these algebras? Okay, good. So there's several interesting special cases of these algebras, but one in particular that I'll focus on for most of this talk is the so-called boundary tube algebra, also sometimes called the strip algebra. So here you imagine that you have two multiplets of boundary conditions, so two module categories in a particular QFT. The reason this is a special case of the previous construction is that you can think of a boundary condition as an interface from a QFT to the trivially gapped theory. And I study boundary changing local operators between boundary conditions in one multiplet and boundary conditions in the other multiplet. And in this situation, I have an action by these sort of horseshoe lassos on these boundary changing local operators. And here again, the algebra that's generated by these horseshoes, we denote as tube B1, B2. And I comment that this algebra has a long history. It's been studied in many different settings, not just in 1+1D physics. For example, this original paper of Kataev Kong, which is the earliest place I found it, studies it in the context of string net models. So it's a fairly rich mathematical structure that appears in several places. Good. So
Question.
yeah.
Hi, Brandon.
Hey, Sahan.
So you said this is a special case of the previous one, right? The boundaries.
Yeah, of this one, yeah.
Right. So boundaries are also some bimodules. So potentially there should be some action also from above in the boundary case.
Yeah, by vec though, so it's sort of a trivial action from above. Like I'm thinking of oops.
Physically, what does it mean to act on above? Because it's empty.
Well, I could think of it as a trivially gapped theory. And the trivially gapped theory is acted on by the trivial symmetry, namely vec. So in other words, indeed, it's a sort of bimodule, but it's a sort of stupid bimodule. It's a C-vec bimodule. But that's the same thing as a C module. So I'm acting by nothing from above.
Oh, I see. Because I thought you want to put the dual on the other side. Is not the dual that you put.
By dual, you mean like
The dual of C with respect to that module category.
Oh, no. This is so here I genuinely have a theory Q and I have nothing on top. So I'm only sort of acting from below.
Okay. Thanks.
Yeah.
This is just a comment, but one other place where these boundary changing local operators show up, actually a really long time ago, is in mirror symmetry, studying boundary changing local operators for in the B model, I think. Yeah, in the B model. It's just another random example.
Right. Okay, good. Thanks for the questions and comments, and yeah, please keep asking more questions if there are any. So good. So we have this this boundary tube algebra, and it acts on this extended Hilbert space of boundary changing local operators. And we want to understand the decomposition of this Hilbert space into irreducible representations of this tube algebra. So how do we do this? Actually, sorry, first I should give you some examples. So one example is the case that you have a theory with a ordinary invertible symmetry that's non-anomalous. In this case, you might have some G-symmetric boundary conditions. And let's say you consider boundary local operators on a single G-symmetric boundary condition. Then you get exactly what you would expect. Namely, this tube algebra is just the group algebra of G. So you just get a sort of standard realization of the G-symmetry. More generally, you might have multiple different G-symmetric boundary conditions. And if they belong to module categories that are inequivalent to one another, then if you study the boundary changing local operators between one G-symmetric boundary condition and another, then the tube algebra won't quite be the group algebra of G in general, but rather it'll be a sort of twisted group algebra by psi. Or the more pedestrian way of saying this is that the G symmetry will act projectively in general. This is sort of the first hint that symmetry in the presence of boundaries sort of behaves differently than symmetry in the bulk. And one more example is that if you have this rep H8 fusion category, which is a particular case of a Tambari-Yamagami fusion category, and you have a theory which has a symmetric boundary condition with respect to the symmetry, then the tube algebra turns out to precisely be this eight-dimensional Katz-Paljutkin algebra. And for example, this symmetry already arises in a very simple model, namely the double dicing model. Great. So we want to understand the representation theory of these tube algebras now. And it'll be useful actually to appeal to the symmetry TFT. And just at a sort of high level, the philosophy that we're going to adopt is that in general, if you have a QFT and you have some p-dimensional objects in it, and you want to understand what the different kinds of representations that these p-dimensional objects can live in are, well, those are precisely labeled by p+1 dimensional topological objects in the bulk symmetry TFT, as was nicely explained in these papers and possibly others. So we'll see how this philosophy sort of is implemented in pretty concrete settings in a moment. So just a one slide reminder of what the symmetry TFT is. The basic idea is that if you have some, let's specialize to 2 dimensions for simplicity, some 2D QFTQ with some symmetry category C, then you can always inflate sort of any picture that you can draw in 2D into a corresponding picture in 3D. And in this 3D picture, you have a topological quantum field theory known as the Tri-Viro theory associated with C. It's compactified on an interval. And one of the boundary conditions of the interval is a topological one, which one typically takes to be this sort of canonical boundary condition that the Tri-Viro theory has, known as the Dirichlet boundary condition. And the other boundary condition is a kind of dynamical boundary condition that depends on Q. And the claim is that when you dimensionally reduce this 3D configuration back to 2D, you get the thing you started with. And the basic utility of this picture is that it often sort of exposes certain kinematic aspects of physics that might be difficult to see in lower dimensions if you hadn't inflated into this symmetry TFT picture. And I just give you an example, a symmetry line of Q in the symmetry TFT picture actually lives on this topological boundary condition. So that'll be important in what follows. Good. So how do you represent boundary conditions in the symmetry TFT? Well, to explain this, so suppose we have a boundary condition B and a QFT Q. Since Q has some C symmetry, this B will belong to some multiplet of boundary conditions, which defines a module category. So so we'll call B the multiplet of this boundary condition B. Now, on general grounds, we sort of expect that when we inflate to 3 dimensions, we get a picture sort of like this. So this boundary condition of Q inflates to a topological boundary condition of the symmetry TFT. And well, which topological boundary condition should we choose? Well, it turns out that the topological boundary conditions of the symmetry TFT are precisely labeled by module categories. And so our basic proposal is that the topological boundary condition that you place here is precisely the boundary condition that's determined by the multiplet to which B belongs. So this is a pretty concrete instantiation of this general philosophy I articulated earlier, that the multiplet to which, in this case, one-dimensional object of Q belongs is described by a topological object of one higher dimension in the bulk symmetry TFT. Okay, and then part of this prescription is that you have to choose a sort of line interface, a topological line interface here between this topological boundary condition B and this Dirichlet boundary condition down here, and also a not necessarily topological boundary condition, not necessarily topological line interface or corner between this physical boundary and this topological boundary. And the basic idea is that, what happens as you swap out this line interface here for a different one? Well, that corresponds to sort of toggling between different boundary conditions that live in this multiplet B. Okay. So yeah, any questions about this, this basic proposal?
I have a stupid question. When you write this equal sign, do you mean that the partition function is equal, or you mean something more?
I haven't specialized too much to a particular partition function, but yes, in particular, you can imagine that like if you have any partition function of the 2D theory where there's a boundary condition, you can sort of locally represent you can sort of locally inflate it into 3D into a picture that looks like this. And then indeed the partition function of this 3D sim TFT will reproduce the partition function of the 2D theory, yes.
Okay, thanks.
Yeah, thanks for the question.
Is this triplet unique? Is it one-to-one, the one you have, what you have written down?
Good. So yeah, so right. So there's some mild non-uniqueness, but I'll say this. So there exists a choice of B twiddle and B such that this does become one-to-one as you sort of toggle this and this. So in other words, like if you fix a multiplet of boundary conditions, that corresponds to fixing these two entries of the triplet. And my claim is that there's a one-to-one correspondence between this choice of topological line interface and boundary conditions B in that multiplet.
Is there some assumption on the simplicity of the two junction interfaces, the B underline and the B tilde?
Yeah, so right, good. So yes, indeed. So for simplicity, let's say we assume that B is simple. We need that to be replicated over here. So in particular, there should not be any you shouldn't be able to draw a picture like this, where you have a topological line and topological local operators that it can end on B underline and B twiddle. Because if this existed, then when you dimensionally reduce it, that would correspond to a topological local operator on B. So indeed, that's a sort of implicit assumption in this, is that this B twiddle is chosen such that this kind of such that you can't draw this kind of picture.
Yeah, because otherwise I would think to have some line that I could fuse with B tilde to change it. But you say if you make that assumption, then you are saying that the B, okay, all of them are B, I don't know how to call them, but the middle, the right B are uniquely determined by the boundary condition.
Yeah, let me just, so you're pointing out that like you could nucleate a pair of lines and then push this on here and then push this on here.
Something like that, yeah, to get another, yeah.
Yeah, the same issue sort of afflicts the standard sim TFT proposal, right? I can nucleate a surface, and then sort of push these onto the topological and the physical boundaries. So there is some sort of hidden a mild bit of redundancy here, but it won't sort of afflict anything negatively that I'm going to say.
I see. Okay, thank you.
Yeah. Good. And just to give a sort of silly example, you can consider the icing CFT, for example, with its Z2 symmetry. This has a Z2 symmetric boundary condition. In the continuum, you would say that it's the Cardy state associated to the duality line. On the lattice, you would say it's the boundary condition where the spins are not pinned; they're free. And when you inflate this into 3 dimensions, what you get in the bulk is the toric code, which is the symmetry TFT associated with a Z2 symmetry. The sort of canonical Dirichlet boundary condition is the standard electric boundary condition of the toric code. And it turns out that because you're considering a symmetric boundary condition, that implies that this boundary condition on the top is the magnetic boundary condition of the toric code. And indeed, because it's a symmetric boundary condition, there's only one boundary in the Z2 multiplet, and that's reproduced by the fact that there's only one topological line interface between the magnetic and the electric boundary conditions of the toric code. Great. So there's one more level of sophistication that we'll need, which is now you want to have a symmetry TFT interpretation of boundary changing local operators. And so here you sort of, we know how various components of the setup will inflate into 3 dimensions. This boundary condition will go over to a setup like on the previous slide. Same for this other boundary condition. The only thing we need to keep track of now is that this boundary changing local operator will inflate into a line like this. And here, O twiddle is a not necessarily topological junction. X here is a topological junction. And so in general, you have a sort of decomposition of these boundary changing local operators into these triples here, consisting of a suitable topological junction X, a topological line interface alpha between the 2 topological boundary conditions B1 and B2 that describe the multiplets to which little B1 and B2 belong, and then this O twiddle gadget. And just because it'll be useful later, I want to give the sort of vector spaces to which these various objects belong names. So this topological junction X will belong to a space that I'll call W alpha. And this not necessarily topological junction O twiddle will belong to a space that I'll call V alpha. Okay, and now, so the point here is that the claim is that if you take the direct sum of these junction spaces over where you sum over these choices of interfaces that you can place here, well, then that defines a Hilbert space, which is acted upon by this boundary tube algebra. And the reason is that, remember how the boundary tube algebra acts. It acts via these horseshoes. But the symmetry lines of a theory, when you inflate to 3 dimensions, live on this topological Dirichlet boundary condition. So they live over here. But now you can see that very transparently, these horseshoes sort of act on these junction vectors X. So this W alpha defines a representation of this boundary tube algebra. And in fact, it turns out that it defines an irreducible representation of the boundary tube algebra, and all irreducible representations arise in this way. So in other words, the irreducible representations of this boundary tube algebra are in one-to-one correspondence with topological line interfaces alpha between these topological boundary conditions of the sim TFT. And remember, these topological boundary conditions of the SymTFT sort of encode the multiplet to which the boundary conditions belong. Okay, so this is a sort of central claim. And now, because every operator O can be decomposed into a triple of this kind, you can sort of decompose the entire extended Hilbert space of boundary changing local operators like this. And written in terms of these W and V spaces, you get something like this. And this may look sort of dense, but I want to analogize it to something that's more familiar. So when you have a finite group and you have some representation R, you can always decompose it into irreducible representations of, of the group. And each will come with some multiplicity Ni. And this is precisely the same sort of equation where this big representation R is this extended Hilbert space of boundary changing local operators. The role of the irreducible representations of the group is played by these spaces W alpha. And you can think of these spaces here, which are, remember, the space of these O twiddle operators, as sort of multiplicity spaces. So in other words, this is sort of keeping track of the multiplicity with which this W alpha arises in this full Hilbert space. Of course, this statement is a little bit imprecise because this is an infinite dimensional Hilbert space, as is this. But for example, if I restrict attention to a fixed energy level E on both sides, then these become finite dimensional Hilbert spaces. And then the interpretation I told you goes through this. The dimension of this thing is precisely the multiplicity with which W alpha arises at energy level E in this Hilbert space of boundary changing local operators. Okay, are there any questions about this so far?
Just one silly one. You wrote that claim in the box. Sorry, I think I missed it. Is that claim claimed by those authors, or is that claim claimed and then proven by those authors?
Good, thanks. Right. So this fact was discovered earlier in mathematical work by these authors.
Oh.
And here we give a sort of physical interpretation of it in terms of the SymTFT.
Oh.
We reproduce the result. And actually, we sort of generalize this kind of result to these more general tube algebras involving interfaces as well. But since it's very similar, but just more complicated, I decided not to present it. So that result about the representation theory of these interface tube algebras is a new result. Okay. How much time do I have? Okay. So before moving on, let me just quickly give you a few applications of this SymTFT way of looking at things. So one application is to RG flows of line interfaces in a QFT queue, or let's say a CFT queue. So suppose you have a CFT with a conformal line interface in the UV and you perturb it by a relevant C-symmetric operator. Well, in the SymTFT, this line interface would inflate similarly to how boundary conditions inflate. So instead of going over to a sort of topological boundary condition of the symmetry TFT, it goes over to a topological interface in the symmetry TFT. And the claim is that this topological surface I that this line interface inflates to doesn't change under RG flows, at least because this local operator that we're deforming by is C-symmetric. And what it means to be C-symmetric in the SymTFT is that, recall that in general, you're attached to a line. This line labels the representation that you transform in, while the trivial line labels the trivial representation. So being C-symmetric means precisely that you're not attached to any line. So you see when you perturb by this relevant C-symmetric operator, you're sort of integrating it along here. You don't touch the bulk surface at all. So the bulk surface remains unchanged, and therefore it should be matched between the UV and the IR. So in particular, for example, if the UV surface operator isn't the trivial surface, then you know that in the IR you must have something sort of non-trivial. It could either be a genuine conformal interface that's gapless, or it could be, unfortunately, a topological line. But you know that if it is a topological line, it must be a line that's not contained in your symmetry category C, because the lines that are contained in the symmetry category are attached to the trivial surface. Okay, so this is one application to line interface RG flows. Another sort of Q application is, suppose you have a symmetry that's non-anomalous, and suppose you have two different C-symmetric boundary conditions, B1 and B2, of your 2D QFT. And suppose further that the sort of multiplets they define, or the module categories they define, are inequivalent. Then the claim is that the Hilbert space of boundary changing local operators, or equivalently the interval Hilbert space between these two C-symmetric boundary conditions, has a non-trivial ground state degeneracy. And the basic reason for this is that you can prove that the dimensions of this generalized, of the representations of this boundary tube algebra always have to be greater than 1. And it's basically because the dimension in this special case of the alpha representation is precisely the quantum dimension of this topological line operator that interpolates between the two gapped boundary conditions of the symmetry TFT. And it just turns out that Feynman dimensions of topological line interfaces between different boundary conditions always must have quantum dimension greater than 1. Okay, so this is a sort of broad set of circumstances under which you can guarantee a ground state degeneracy of boundary changing local operators. Great. So how can we probe this decomposition of the Hilbert space into irreps? Well, the way that we would like to do this ideally is to define suitable symmetry-resolved partition functions. So in the case of boundary changing local operators, let's say you're in a CFT, by the state operator correspondence, they correspond to states on the interval. And so if you want to count such states, then you're led to consider the annulus partition function, which is just the interval times S1. So there's two different ways that you could incorporate symmetry into your analysis of the annulus partition function. So one thing you could do is you could form a generating function which counts sort of, at each energy level, how many times the irreducible representation W alpha appears in the spectrum at energy level E. And so we'll just give this class of partition functions a name. We'll call them the representation basis partition functions. If you like, you can represent this partition function as a suitable partition function of the symmetry TFT on a particular background. But we won't use that interpretation too much. Another natural way that you could sort of soup up your annulus partition function with information about the symmetry is you can couple it to a background gauge field. And by Poincare duality, basically, coupling your theory to a background gauge field is sort of the same thing as putting basically topological line defects on the annulus. And so in this case, you're led to consider these kinds of partition functions, basically the annulus in the presence of a line operator that stretches from one boundary to the other. And if you take time to run along the circle direction, then you can express this as a trace over this Hilbert space of boundary changing local operators, where you've inserted one of these sort of lasso elements of the tube algebra into the trace. And to distinguish this class of partition functions from the previous class, I'll refer to these as the symmetry basis. Even though these two things look sort of naively like they are two genuinely different ways that you can probe the symmetry of a theory, they're actually basically equivalent to one another. For example, in the case of a finite group symmetry, here you're basically taking traces of the group element over the Hilbert space. Here you're counting multiplicities with which representations arise. And famously, these two things are equivalent to each other. If you know the traces of group elements on the Hilbert space, you can decompose it into irreducible representations, and vice versa. If you know the decomposition into irreducible representations, then you can reproduce all the traces. And the machinery that allows you to sort of go back and forth between these two different classes of partition functions, in the case of finite groups, is character theory. And so our goal is to kind of develop an analogous understanding for these tube algebras, which encode how non-invertible symmetries act on boundary changing local operators. So our goal is to develop a kind of character theory in this setting. So I want to make a brief interlude and describe some important numbers that are basically going to be ubiquitous in everything that I have to say from now on. So these are the so-called half-linking numbers. A special case was studied in this very nice paper. So the definition of these numbers is as follows. Don't worry about all the detailed indices and things like this. This is just to sort of give you a sense for what they look like. The idea is you have sort of above the page, you have the symmetry TFT. And the page itself defines a kind of boundary of the symmetry TFT. And that boundary is divided into two regions by this blue line here. So one region you place in a boundary condition B2, the other region you place in a boundary condition B1. And interpolating between these two boundary conditions, you are allowed to use these topological line interfaces alpha and beta. So these are sitting on the boundary. Likewise, these black lines here are also sitting on the boundaries. A is sitting on this B1 boundary, B is sitting on this B2 boundary. And then finally, you have this bulk line mu, which sort of links with this topological line interface. And the reason that this picture defines a number is that you can sort of shrink this configuration of lines down until it looks like a point. So it's a topological point operator sitting on this boundary condition, in this case, the B1 boundary condition. And if you assume that this B1 is an indecomposable boundary condition, then the only topological point operator on it is going to be the identity. And so you simply define this number to be the whatever multiple of the identity operator you get when you shrink this configuration of lines. They're computable in certain cases. For example, if C turns out to be a modular tensor category, and B1 and B2 are both the Dirichlet boundary conditions. So this is, for example, the situation that you're in when you study diagonal rational conformal field theory. Then it turns out that you can express these half-linking numbers in terms of the F and the R symbols of the category C. And the F and the R symbols are sort of known for a broad range of categories, so you can actually compute these half-linking numbers pretty explicitly. And we do this in our paper for the special case of the Fibonacci category. More generally, in examples, these things should certainly be computable, and I think it would be very interesting to develop techniques to better compute them. But for the purposes of this talk, I'm just going to assume that they're a sort of resource that's given to me by by God, or like an infinitely powerful oracle. So I'll assume that I have sort of complete control over these half-linking numbers. And I want to show you how a very broad class of kinematic calculations that you might want to do can sort of be expressed in terms of these numbers that are associated to the symmetry C. This is just to sort of emphasize the ubiquity with which they show up in various calculations, but maybe for interest of time, I won't explain this in any detail. This is just to say that various manipulations that you do in the symmetry TFT often feature these half-linking numbers in some way. So for us, the most important place that they'll show up is in the character theory of these tube algebras. So how do we define these characters? Well, we have these we have these representations W alpha. And so remember that these W alpha were spaces of junction operators in the symmetry TFT. But by the state operator correspondence, these spaces of junction operators can also be expressed as the space of states of the symmetry TFT on a particular disk configuration. The details of this state operator map are sort of unimportant, but the upshot of it eventually is that if you want to take a trace over these tube algebra elements within these representation spaces W alpha, then it turns out that you can express this trace as a particular partition function of the symmetry TFT on a solid torus where you've inserted various lines. So here, if you like, the sort of lasso element is living over here. Remember, the lasso sort of looks like this. And here it ends up appearing kind of stretched out into a straight line. Anyways, again, the details here don't matter, but this is just to show you that there's a well-defined partition function in 3D TQFT that you can compute that defines the characters of this boundary tube algebra. And in fact, it turns out that if you use these half-linking numbers that I wrote down earlier, these characters admit a nice expression in terms of those half-linking numbers. So in other words, if you have control over these half-linking numbers, then you have complete control over the character theory of the boundary tube algebra as well. And I comment in passing, although I won't have the opportunity to explain the significance of this fact here, that this is a sort of very vast generalization of the Verlinde formula. Indeed, in the special case that you specialize C to be a modular tensor category, and you take both of these boundary conditions of this symmetry TFT on the solid torus to be Dirichlet, then it turns out that these three psi entries all become basically the S matrix. And then it looks exactly like the standard Verlinde formula. Okay, and so good. So these characters should behave in most ways like the characters of a finite group. But most importantly for us is the fact that they enjoy a very nice orthogonality relation. So, for example, in the special case that your symmetry is actually just vec G, in other words, an invertible symmetry described by a finite group G, and the boundary conditions that you're considering are G symmetric, then this orthogonality relation precisely reduces to the standard orthogonality relation that we know and love from the character theory of finite groups, which says that the sort of inner product of two different characters is a delta function. So this is a sort of a generalization of ordinary character theory. And this orthogonality relation has a lot of useful implications. Let me plug in my iPad before it runs out of juice. Good. So are there any questions so far?
So the existence of this character theory and the orthogonality is basically coming from the semi-simplicity of all the input categories, right? Can you phrase it that way?
Yeah, I haven't thought much about the non-semi-simple setting, but yeah, I guess that I could imagine that is an essential assumption, but yeah, I haven't thought
I mean,
much
I'm
about
just wondering, is all of this just like some souped up version of like Artin-Wedderburn theorem?
Good question.
Like, why do we need like braided tensor categories and things in this story? Is it just something about semi-simple rings?
Yeah, that's a good, good. So you're asking, like, ordinary algebras also have maybe a character theory, and is this just imitating that? And the honest answer is I don't know, because I haven't studied the character theory of ordinary semi-simple algebras. But I would say that one of the nice things about this is that this character theory can be uplifted into physics in a sort of nice way. In other words, like, most of the calculations you do have can be represented as sort of calculations that you can do in 2+1D topological field theory. And so for that reason, you might imagine that they're under somewhat better control, might have more special properties. And well, also the pictures sort of help guide our intuition about how to handle them. But I think it's early days for this, so I don't have anything terribly concrete to say, unfortunately.
Thanks, though.
Thanks for the question. So good. So how can we use this? Well, so now we can simply use this to relate these two bases that I had told you about earlier. One was this basis which sort of counts the multiplicity with which the alphath representation of the boundary cube algebra appears in the spectrum. And the other was this basis of annulus partition functions, which are decorated by the insertion of a topological line operator. And as you can see, they're related by a very simple linear change of basis, featuring these characters that we defined earlier as the coefficients of the basis change. And so a cute setting in which you can apply this this sort of program to its completion is the setting of diagonal rational conformal field theory, where you've chosen C to be the category of Verlinde lines. In other words, the category of topological line operators, which commutes with the maximal chiral algebra, and where you've chosen these multiplets of boundary conditions that you impose at the boundary of the interval to be the multiplet of the Cardy boundaries. So these Cardy boundaries are boundary conditions that preserve this maximal chiral algebra of the RCFT. So in that case, it turns out that you can compute these representation basis partition functions exactly. There's literally just the characters of the chiral algebra, and those are known for a wide class of chiral algebras. And these other characters, chi of the boundary cube algebra, admit closed form expressions, as I was saying earlier, in terms of the F symbols and the R matrices of C, because C is a modular tensor category. And therefore, this equation sort of tells you how to compute the annulus partition function of an arbitrary diagonal RCFT with the insertion of arbitrary Verlinde lines, purely in terms of basically the characters of the chiral algebra and the F and the R symbols of the category Verlinde lines C. Another kind of nice application of this technology is to orbifolds. So let me remind you that the difference, well, the symmetry TFT representation of an orbifold of a theory Q by some algebra object A, well, it mostly looks the same as a symmetry TFT representation of just Q, but the difference is that we swap out this Dirichlet topological boundary condition for a different topological boundary condition that's labeled by this algebra object A. So this makes it clear that the only difference between Q and any of its orbifolds has to do with this, the physics near this topological boundary condition. And the physics near the physical boundary condition is the same. But on the other hand, you'll remember that these representation basis partition functions are precisely counting these local junction operators, O twiddle, that live on this physical boundary condition. And so for that reason, the representation basis partition functions of Q and of any of its orbifolds are actually the same. On the other hand, the annulus partition functions where you've inserted lines will generally be different between Q and its orbifolds. But using our character theory, we can relate these to the representation basis partition functions, which are known. So in particular, if you sort of chase the formulas that we've written, then what you find is a kind of nice formula which relates all the sort of twisted annulus partition functions of an orbifold to the annulus partition functions of the original theory, with some coefficients which are basically come from the character theory of these boundary tube algebras. You should compare this kind of formula to a sort of celebrated, well-known formula that applies to the torus, which says that the torus partition function of an orbifold is sort of obtained by summing over line insertions along the various cycles of the torus, in the case that you're orbifolding a finite group. Okay, and then maybe one more thing I'll mention before concluding is, so another thing you might try to do is to compute the asymptotic density of states on the interval within each charge sector. So now suppose we have a CFT. The interval Hilbert space decomposes into representations of the boundary tube algebra, and therefore you can label the states by the representations. And you might ask if there's any universal physics which governs the asymptotic density of states within individual charge sectors. And in the case of the asymptotic density of states on the circle, this basically, when you don't incorporate symmetry, this result that establishes this universality is known as the Cardy formula, and it uses modular invariance. So in the case of the annulus partition function and the asymptotic density of states on the interval, we have to use open-closed duality. So open-closed duality basically asserts that if you take time to run along the circle direction, or you take time to run along the interval direction, those results should agree. And in particular, along the circle direction, you get sort of the kinds of expressions that we've been working with so far. You get traces over the interval Hilbert space. Whereas when you take time to run along the interval direction, you naturally express the annulus partition function as overlaps of boundary states. And well, I won't go through the details of the derivation, but essentially what you can imagine is that we can use our change of basis formula to, along with open-closed duality, to compute the high temperature limit of these representation basis partition functions that keep track of how many states there are within a given charge sector. And this high T limit is sort of the thing that ultimately leads to the asymptotic density of states. And so I've written it here just so you know that it exists, although I won't have time to explain sort of the more detailed features of it. Okay, and so I'm about ready to conclude. One thing I'll say is that I didn't have time to discuss the annulus partition function in the closed string channel and the analysis of the sort of corresponding twisted boundary states. This is a really nice story. And well, so I recommend you read the paper if you're interested in it. For the future, the one clear thing to do is to uncover more applications and just do more examples. As I said earlier, it's sort of early days for this character theory, and it could well be related to known mathematics. And so establishing that connection would be useful, although I still think that it's potentially interesting in this more restrictive setting still because of the connection to topological field theory. And finally, I think it would be interesting to learn how to compute these half-linking numbers in concrete examples, besides just the case where C is a modular tensor category. And so with that, I'll conclude.
Thank you. Do people have questions now that we've reached the end? Yes, no.
Here's another question. Maybe you explained this when you talked about the quantum dimension of the boundary changing operators being greater than 1. Is there an algebra that you can say acts somehow, like some kind of projective symmetry action on that, on the boundary condition changing operator?
Is there a projected algebra that acts on the? Well, I guess it depends on what you mean by the. So you're asking, sorry, you're asking about boundary changing local operators, right? Just to be clear.
Yeah. So I mean, one example where this happens is when you have like different fiber functors of vec G, right? About those as kind of 1D SPT phases and the interface between them. That space of boundary changing operators is the edge mode where you have the projective action.
Yep.
And yeah, you could ask the same question about fusion category SPTs.
Yeah.
Their interface has some quantum dimension more than 1. I just don't know what acts projectively there.
Yeah, so this is supposed to exactly be, I mean, this is exactly what that is. So the way I would describe it is in the situation that you said, where you have two different fiber functors of vec G, then this boundary tube algebra that acts is the twisted group algebra, is a sort of is a twisted group algebra, which is the same thing as saying G acts projectively.
Yes, absolutely. But in the fusion category case, I don't know what it's going to be, an ordinary kind of algebra that acts.
Yeah, it's an ordinary kind of algebra, and it's precisely this boundary tube algebra. I don't know that there's as clean of an interpretation as, like, the boundary tube algebra is a kind of projective version of some other algebra. I don't know that kind of interpretation.
Yeah, you probably can't say that, no, but yeah, I guess you do know its representations are all more than 1 dimension.
Yeah, exactly. So that's what the slide was establishing, that its representations are all greater than 1-dimensional.
Okay, thanks.
Yep.
Right. I will stop the recording.